I think I should start, or?
Yes.
Okay, so hello everyone. My name is Safak Arslantürkoglu. I'm a PhD candidate at ETHZ Zurich at the chair of Structural Dynamics and Earthquake Engineering, led by Professor Stoyadinovic. Today I will start by discussing the characteristics of the 2023 Maraş earthquakes and briefly overview the history of Turkish seismic codes. Then I will talk to you about how masonry buildings perform throughout the Turkey earthquakes. Before I do that, I want to thank Dr. Zeynep Ünsal Aslan. She was a part of our team in Turkey, and we worked together to prepare this presentation. Let me start. The 2023 Turkey earthquakes were a series of seismic events with significant magnitudes. The shakings took place along the East Anatolian fault line. The main earthquake, which struck on the 6th of February, registered a magnitude of 7.8, followed by an aftershock about 10 minutes later. Another major aftershock occurred about noon with a magnitude of 7.7 and tragically led to additional collapses of many buildings that initially survived the main shock. As illustrated by the spectral acceleration levels derived at the stations in Hatay and Kahramanmaras, the acceleration levels exceeded the 500 years code spectrum for a large period domain. In Hatay, even the maximum considered earthquake with a return period of 2,500 years was exceeded for the major portion of the period range, which may explain the devastation in this region. Looking at the previous earthquakes in the last 100 years in Turkey, the country has experienced on average a destructive earthquake approximately every 3 years, and the evolution of the codes has been strongly correlated to them. In 1940, just 1 year after the devastating Erzincan earthquake, the first seismic code was published, which was a translation of the Italian codes. In 1968, significant updates were made, particularly in the dimensioning of concrete members. Until then, the provisions mainly address timber and masonry buildings. An elastic design spectrum and capacity-based design regulations were introduced by the 1998 code. The 2007 code introduced assessment and retrofit of existing buildings, as well as displacement-based approaches. The code used today is from 2018. The two design approaches are treated in chapters 4 and 5. Chapter 4 dealing with the conventional force-based capacity design regulations based on linear analysis, and chapter 5 nonlinear analysis procedures. This code also includes an extension dealing with special topics such as chapter 13 devoted to high-rise buildings or 14 base isolated buildings. The definition of seismic hazard characteristics is one of the key improvements in the new codes. Before 2018, the country was divided into seismic zones, as in Switzerland, according to SIA 261, each with its own PGA value. With the new seismic hazard model, the analysts can extract location-specific acceleration coefficients for different hazard levels using this web tool provided by ETHZ. By doing so, short periods and 1 second periods accelerations are obtained to plot the design spectrum. And performance targets for the design and assessment, these are defined based on damage states and seismic design categories associated with the spectral accelerations. For the building design, excluding high-rise buildings, the ordinary performance target is set to controlled damage state under the design earthquake that dictates a limitation of plastic deformation in structural members and sort of represent the life safety performance targets. And to reach this target, the code allows the employment of force-based procedures. For critical buildings with vital importance, such as hospitals, advanced performance targets are set for the limitation and control of the damage. And in that case, displacement-based methods are prescribed. And for the assessment, the code again prescribes displacement-based procedures, regardless of the importance class, to aim controlled damage limit state with refined targets for critical buildings. In this part, I will try to show you some photos of masonry buildings we shot during our stay in Turkey. Residential masonry in Turkey are not as common as in Switzerland. They are usually low-rise with 1 or 2 stories and mostly limited to rural regions or historic town centers. In the small village, Gençobası, many residential houses were constructed using concrete blocks or RC slabs. These are unengineered buildings constructed by the owners only. Here, the exterior wall suffered diagonal shear stepping cracks, beginning at the wall center with a crack pattern through the mortar propagating towards the corners. And the same wall from the outside to display the brick pattern and the separated wall parts moving away from each other. In Gençobası, most of the non-residential buildings were made of adobe, such as this barn here. The corner wall is disaggregated as a result of poor unit quality and the lack of connection between the corner walls. Here, the roof structure is made of light steel sheets, failing to constrain the wall against actions perpendicular to the plane of the wall. Another failure at the barn entrance near the door opening with irregularly placed mud bricks, and again a lack of connection between wall layers here intensified the out-of-plane problem. Buildings with flexible floors, usually those with timber beams, often showed an out-of-plane behavior due to the lack of floor-to-wall connections. The self-weight of the panels often resisting and overturning moments, they were not sufficient to withstand the out-of-plane actions. On the front side of the same building, a vertical triangular hinge has formed in the middle of the adobe wall, and here vertical cracks implying an in-plane mechanism beneath the roof that rests directly on top of the facade wall. And here a rigid body motion showing a clear out-of-plane rotation of the facade wall with a hinge formed on top of the ground floor. In our last 2 days, we spent most of our time in and around Hatay. Occasionally, we observed ring beam-like elements generally built out of the same units as the wall. Their presence is characterized from the horizontal cracks and distinct separation along the panel. Here is an example of the disintegration of large masonry units from a building in Arsus. Again, another example from Arsus showing a combined in-plane and out-of-plane mechanism. The in-plane actions causing a diagonal crack in this wall were likely followed by an out-of-plane action following the aftershocks. Here is a before picture of a hotel that developed a global out-of-plane mechanism. The failure is characterized by the overturning of this entire wall. The collapse was initiated by vertical cracks at the connection of the facade with the orthogonal neighboring wall. And this type of a failure is a stability failure rather than a strangulated material failure. And on the upper floors, we could observe steel beams of the floor system, likely stemming from a recent restoration, which was not sufficient to provide an improved behavior and prevent the out-of-plane failure. Further examples illustrating wall floor and wall roof details in most of the cases, with one-way timber beams with a single layer of wood planks. In case of the lack of mechanical connection through anchoring elements, such as the case on the right top picture, the sole resistance is coming from the friction between the timber beams and the walls. The last examples are from Antakya with upper story failures, which may have happened due to the very high vertical components of the ground motions. This building suffered a roof collapse and lost its upper story, likely due to the uplifting of piers and the resulting reduction of the shear capacity. Another building is a stone masonry example from 1911, the Affan Cafe or Affan building. High tensile stresses in the upper floors may have triggered the failure in the second story. And to conclude, let me summarize my points. A number of reasons contributed to the extensive damage levels in the affected regions. An indicator of the significant role of the soil was the concentrated damage pictures. We've seen damages on one side of the street, while on the other side of the street building were standing. Another point, in buildings with flexible floor diaphragms, out of plane was the most common failure mode. One potential reason is the inadequate structural detailing, such as the lack of steel ties or ring beams, or also other type of anchorage elements. Residential low-rise buildings with concrete slabs were generally capable of exhibiting a global in-plane behavior, and they were able to provide their structural or maintain their structural integrity. And as the last point, local behavior is frequently the weakest link when dealing with masonry with flexible floors, considering that most of commercial software assumes structural integrity of the building. Out of plane remains an often overlooked part in engineering practice. However, the recent series of Turkey earthquakes once again pointed out their relevance in the evaluation of existing buildings. This brings me to the end of my presentation. On behalf of our team members, I would like to thank SGEB for the invitation and also thank the audience for their attention. Thank you.
Thank you very much for the interesting presentation. Then, yeah, I think we could go right away to Nikola. There was one question. The recording will be available on our website, just for information, if all goes well, technically.
I'm recording, so hopefully it's going to work out. Let's see. So let me start with my presentation. Hello, everyone. My name is Nikola Blagojevic. I'm a postdoctoral researcher at the chair of Structural Dynamics Engineering with Professor Božidar Stojadinovic at ETH, like Safak. And here today I'll present two topics. The first one is going to be the performance of RC structures that we observed while we were there in March this year. And the slides which I'm going to be using are created by members of our team, Nemanja Krtinić from University of Ljubljana and Professor Marko Marinković from University of Belgrade. So let me just see if this is going to work out. Yes. So when we were there, our impression was that most of the buildings are reinforced concrete structures. And if we look at the statistics, we actually see that 50% of households are situated in buildings built after 2001, so fairly moderate structures. And we also see that 86% of buildings, let me see if I can get the point. Yes, 86% of buildings are reinforced concrete. And so these buildings that we saw, this is one possible classification. So we saw RC frame systems, we saw reinforced concrete frames and some shear walls. We also saw buildings that had dominantly shear wall systems. Then there were some flat slab systems and something that's special for Turkey, these tunnel form buildings, which are built as social housing, built by the state, and they have a significant amount of shear walls. And we can kind of group the damage types that we saw there into these 8 categories, which you can see here. And in this presentation, I'll briefly illustrate some of these damage types, but you can also hear more about them in a longer ETH/SUSI webinar, which is already on YouTube. And at the end, I'll provide some more information. So let's start with this building here. This is, I would say, a typical building which we saw in the area. It's built in 2019. It's RC frames with some shear walls, and you can see the before and the after photo. So this building here collapsed, while this building here has some infill damage. And if we go, when we went inside the building, just see why this does not work. This is what we saw. So buckling of the reinforcement, poor quality of the concrete, as you can see here. And if you zoom in, you can also see that these stirrups are overlapped at 90 degrees, which is not the best thing to do in seismically active areas, because then they open up fairly easily and there is no more confinement provided by these stirrups. Another thing we saw often were soft story mechanisms. And here is an example of a before photo from a reinforced concrete building in Kirikan. So 4 floors in total, a rectangular plan. but you can see that on the ground floor, we have a garage, so not a lot of stiffness here. And then these floors are much stiffer than the ground floor. And then this is what happens. And especially in this direction, parallel to the street, because I assume the stiffness is much lower in this direction, because in the longer direction, there is more room to place more walls. So there is more stiffness. So usually these buildings would collapse in the shorter direction, especially if there are also some walls on the back side of this building. So there is additional torsion while these buildings are oscillating. We also saw some shear wall buildings. Here you can see the before photo of two identical very similar buildings, one next to each other. And here the ground floor dimensions are 20 by 18 meters. And this building was built in 2008. So also a fairly new building. And this is what happened after. This building here collapsed, despite these huge shear walls, which we can see in this direction. My assumption would be that in the other direction, parallel to the street, there were not as many shear walls. And if we see the other building that's left standing, that's the one behind, you can see that there is still some infill damage. And we also went around this building. So on the back side of this building, this is how it looks. If we zoom in, we're going to see significant damage of this beam going into the wall, and also rebar rupture. So the forces must have been pretty high to cause this rebar rupture here. This is at the bottom of the wall. And we also saw reinforcement buckling on this side. And so this is the direction parallel to the street. Short column effect, this was also quite common, especially if you have these small windows, which then change the height of the column in a sense. And this is a building in Nurda. If we zoom in, we see what happened here. So these elements usually experience quite large forces because they have increased stiffness due to their small height. So with the same displacement, they get a lot of forces. And then what happens, in this case, what happened, we have significant buckling of the longitudinal reinforcement. Once again, we see that what happened with the concrete crushed in these very large chunks, and stirrups opened up, although from what my colleagues saw in this case, they were properly overlapped with 135-degree hooks. This was not enough to prevent the opening of the stirrups. And here, I forgot to mention, here you can see the accelerations of the closest seismic station, so quite high PGA here. And this is the stirrup distance, 15 centimeters. Overturning, this is something that we saw in Antakya in a couple of buildings. So here is one example. This is a reinforced concrete frame building, 8 to 10 years old. We were told this is one of the most expensive buildings in Antakya. And as you can see now, it's horizontal. If you look at the bars, so these are the ends of this is the ground floor. So this is the connection between the ground floor and the base slab. You can see this looks to me like not sufficient anchorage of the longitudinal bars, and so they could easily pull out once this building started to shake. This is an example of a health center. So let's say an important building, although a private health center built last year, 2022, and that experienced a significant damage of the infill walls. If you look at here, this whole facade is out. So, and this is out of plane collapse, as you can see here. And what our colleagues noted is that here, the connection between this wall and this slab here is foam. So there was not a lot of strength in this connection. But in general, what my impression was while I was there, that the damage of the infill walls was very, very widespread, especially in reinforced concrete frame buildings, which are very flexible. And so once they start to shake, they consume the earthquake energy by displacing a lot. And infills don't have the displacement capacity, so they often break. So here is, if we zoom in here, and so then we have this out of plane collapse, which is sometimes just out of plane, but also what happened is you have this interaction between the in plane and out of plane, like Safak mentioned. So your wall gets damaged in plane, and then once the building starts to shake in a different direction or a slightly different, then it just falls out. And this is how these this damage of the infill look inside when you step inside the building. So we also saw a couple of buildings which were structurally pretty fine, not a lot of damage they were usually RC frame buildings, but significant infill damage. And then this prevents people from staying here, of course, and then they, even if you repair these buildings, it's unsure if they want to go back to live in buildings where they saw that this happened. And now coming to the tunnel form buildings, which did quite well in this earthquake from what we heard, because they have this shear walls and a lot of shear walls because of the way of they were constructed. So they did not really, I don't think they collapsed, or maybe there were very few cases which collapsed, but what we saw was still some structural damage, which was in some cases significant. So buckling of the rebar, rupture of the rebar. So even if you have a lot of shear walls, detailing is still important to make sure that these things would not happen, although this was a strong earthquake, so this might be justifiable from a risk perspective. And now I would like to just briefly mention what we observed regarding the infrastructure and the recovery efforts. Although this was not the main focus of our trip, we did manage to see a couple of bridges of water towers to understand how functional these cities are now after the earthquake. And this is an example of a bridge or a highway overpass that's reinforced concrete. And most of these bridges were prefabricated reinforced concrete girders, where most of them were in use. I think only 2 bridges collapsed out of 1,000 in this region. And this is one that we observed, which was in use despite this damage that you can see here. We saw displacement of around 20 centimeters of the bearings. And also most likely these girders were pounding against this part of the abutment, causing these cracks and these damages, which you can see here. And when we went to Antakya, this is the city center, which experienced significant damage. And here is the bridge in the city center, which is in use and looks quite okay. Most of the damage is located at the end of the bridge, as you can see here. And here's an example of a water tower. We saw a couple, and here is one near Arsuz, quite high PGA, 0.45 G. And this tank was full during the earthquake, so there was even more mass that was moving. And the water tower was painted before the earthquake. So all of this damage that you see here, this is all only from the earthquake. So we see a lot of spalling that revealed the corroded rebar and a lot of damage at the base of the columns, you can see here, as well as in the connection between the columns and these ring beams that are used to stiffen the columns. And it was out of service because these pipes broke here. And once they were repaired, I think they started using the water tower again. Coming back to the functionality of these neighborhoods and these buildings. So what we saw in Skanderun, for example, are these neighborhoods where some of the buildings look fine, minor damage, but then surrounding buildings have significant damage. And what we found out from the locals, this is just based on interviews with the populations we met on the street, they said that in such neighborhoods, they don't have access to gas or to electric power or to water because the municipality shuts off the access to these utilities because of safety concerns, because these buildings are being demolished and debris are removed. So even if you have a very well-designed building, but buildings around you are not that good and they suffer extensive damage, your building's functionality might still be reduced. And then if we go to a different neighborhood where there was no damage, what we found out by talking with people was that these buildings do have access to gas and I think also to power. I think this is what we were asking them. And this is the same city. This is maybe 15-minute walk from here to here. Also, we saw a couple of buildings that were functional despite the damage, which was mostly non-structural. So here we can sort of assess what kind of damage is acceptable to the owner, so that they would open up a bakery or a cafe and still operate in this building, allowing for some of the local economy to be restored. What we also noticed while we were there, this was a month and a half after the earthquake, that most of the recovery efforts were focused on demolition and debris removal. There were a lot of trucks going around taking away the debris. And what we also found out was that at that time, there were no clear reconstruction plans. So owners did not know what they want to do. There were some owners that were taking the initiative and already developing new plans for the new buildings, but most of the owners were still waiting for government instructions. And then this causes additional uncertainty and delays the recovery of these cities. And so what we're doing at ETH, we're developing tools, software, which we can use to design reconstruction strategies and then help the administration of this cities plan their recovery in a way that's going to be efficient, considering the availability of local resources, finances, and also trying to build back better. So in the future, these things wouldn't be as damaging to the community as they are now. And just I want to finish off here. I would point you to some more resources. So we have the ETH SUSI webinar is online on YouTube. You can see the whole thing. It's around 2 hours where we go into much more detail than we could go here regarding the time constraints. There is also the ERI webinar series, which is also quite good, goes into even more detail than we do. And then there are also a lot of reports. I listed some here, which can also be quite beneficial if you want to understand this earthquake better. And I would stop here. I will be happy to take any questions. I guess we'll do this later after the last presentation, and thank you for listening. Just stop sharing.
Well, thank you. So I'll try again. Thank you both for the interesting presentation. So maybe just, I forgot to give the background initially, but so Nikola and Safak, you were in Turkey in March, right? Mid-March for a week? Or so?
Yes, yes.
And then with the ETHZ mission, and then Ufuk, I think you told me you spent quite an extended amount of time in the earthquake region. So we're happy to hear from your experiences.
Yes. So actually, I visited the earthquake site at the second day of the earthquake. We were called there to inspect the hospitals for the critical response facilities. And then in total, I had 4 visits, which spanned a duration of 3.5 weeks in total at the site. So shall I start with the presentation?
Sure, go ahead, thanks.
Okay, thank you. So in this presentation, of course, I have been to the region for quite a long time, but I would like to summarize the lessons learned to a short time interval as possible to give the key points. And I am a member of the Department of Earthquake Engineering at the Disaster Management Institute at Istanbul Technical University. So, and I'm proud to be here with such a distinguished set of experts, presenters, and the audience. Thank you for this opportunity. So, basically, in this presentation, I would like to focus on what are the implications of this observed damage at the site to the future design codes against seismic actions. While drafting this, I started thinking, what are the fundamental things that are not going to change about how we design those structures? We, as the structural engineers, trying to provide the sufficient strength, stiffness, information capacity, robustness, and energy dissipation capability to achieve the desired performance as economically and sustainably as possible. So that's our objective. This objective was there since over thousands of years, and this is going to stay. But then, while trying to achieve this objective, inevitably we introduce some simplifications, some idealizations along the way. And these idealizations are most of the time simplifications of the reality. Post-earthquake reconnaissance missions are quite valuable opportunities to observe how these idealizations that we introduce, how they reproduce reality and how they're far away from the reality. I try to summarize my observations with that. So as fellow speakers also mentioned, this earthquake sequence was essentially composed of 2 main shocks that were separated with a time interval of 9 hours, and they basically generated a number of further aftershocks. Each main shock triggered their own sequence of aftershocks. And as a result, there were a very, very large number of aftershocks affecting the activity in the region. And what became apparent for me after this earthquake, based on the interactions with the geologists working in the region, was the fact that essentially for such large earthquakes, it's very common to have a severe distortion of the tectonic plate boundaries, and it's kind of expected to have these subsequent main shocks in the neighboring fault segments. So basically, they inform me that such doublets of earthquakes are rather observable under such extreme events. And specifically for the sequence, basically everything had started from a relatively small fault segment and spread over the large East Anatolian fault over here. And then after 9 hours, this segment was ruptured. And you can see the cities that were located all around these rupturing faults. And well, after having this idea of two main shocks taking place with a relatively short time interval of not only 9 hours, I became interested in what are the amplitudes of grand motions that were registered during these two main shocks. What are the consecutive shakings that were exhibited by the buildings? Because as engineers, we typically focus on the main shock event and try to estimate the amplitudes of that event individually and try to make sure that the performance is achieved for that main shock. However, for the case of such doublets generated after large earthquakes, the situation becomes a little bit different, basically. Here you can see the scatter plots of the accelerations registered at different stations. In the horizontal axis, you can see the PGA of the peak grand acceleration of the Pasajik earthquake, the first one. In the vertical axis, you can see the peak grand acceleration registered during the second main shock event. And you can see that the stations that are located with the data point located along the diagonal are the ones that almost registered the same level of shaking consecutively with a time interval of 9 hours. And among these, one of the high intensity ones was this 4611 station at Chalaya and Jerit. So it's located here, and as expected, it's located almost equidistantly from the two planes you can see. That station had registered a PGA of 0.36 G in the first main shock, which was followed by a subsequent shaking of 0.2 G. So essentially, I started thinking when I was working on the site, this has quite an implication on earthquake engineering. So because when such earthquake grand motions are repeated over such short time intervals, and when the second event are some causative events that are triggered by the first main shock, essentially for the performance assessment of any design we would have for such a large main shock should include the effects of this one, which is a natural outcome of the essential main shock we have. This problem was essentially something we have been working on in our group for some time. So the progression of the damage with the aftershock sequences and subsequent shakings related to that. But in our analysis, we were assuming that essentially we will have some sufficient time for the evacuation and sufficient time for the inspection of the damage itself. It looks like in some of the events related to very large earthquakes, we may not really have the time to assess the safety of the damaged structures within the sufficient time interval. And as engineers, then, if we are going to verify the performance of our structures against such high intensities of shaking, high-intensity shaking events, we should consider the entire sequence of events in total, because they will be the set of events that will be experienced by our structures. But this is not a very easy task. The research shows that the likely range of residual displacements and residual stiffnesses that are attained at the end of the first main shock has a critical impact on the likely performance that will be exhibited during the second event that's going to arise. And unfortunately, that's not something easy to capture, their set of residual displacements. We were able to do a quite good job in estimation of the maximum displacements based on the past research we have done during my time at ETH Zurich in the group of Professor Dazio. We are quite good with that. However, for the case of residual displacements, unfortunately, our current tools for modeling the seismic response of the structures that are deforming in the inelastic range, they have very limited accuracy, unfortunately. The residual displacements and the residual stiffness that are sustained are very sensitive to the small cycle response that is very poorly calibrated. Therefore, as this engineering geologists are working on identifying the specific hazards that will, specific reasons for observing the earthquake doublets, from the structural engineering side, probably we also need to improve our modeling tools to be able to capture the responses of our structures under such repeated excitations. So we need to develop our tools to provide better predictions about residual member stiffnesses and strengths, residual difference amplitudes, and damage periods and damping ratios for the structures, so that we are able to see the full performance of our structures under the expected sequences. Another thing that caught my attention during our reconnaissance visits to sites was the signs of severe vertical excitations. Here you can see an RC structural wall building that was damaged in Antakya, Hatay, which was at the very south edge of the rupture we had during the Pazarcık earthquake, the first main shock. And in this building, what was kind of interesting was that there was systematic failures of the connections at the connection regions for these relatively short beams that were supporting this overhanging slab. And essentially, these were very systematic. So in almost all of the hinges, you could see some flexural damage that were triggered. So since this beam was a relatively short cantilever beam that didn't support any other element in the free end, just the floor slab, I started thinking that should be quite a vertical excitation demand that should be experienced at this site to trigger such level of flexural damage in the cantilever beams hanging out from a building. And then a few meters away from that building, we also came across this damaged building, which indicated quite severe damage in the plastic hinge regions at the bottom of the ground story columns. And from this damage, of course, it's difficult to see what was the progression of the damage during the loading. And it is possible to easily observe that the confinement of the detailing itself, the reinforcement detailing at this zone was kind of poorly handled. It didn't really obey the codes, but one could also see that such a widespread damage could also be triggered due to high demand in terms of axial loads in the region. Also for this building, we could observe some interesting patterns of damage at the top of the reinforced concrete walls, where again the cantilever beams were connected. So when we inspected those regions, one can really see a very dense congestion of the reinforcement that would probably trigger a weak layer of reinforcement. But then also this systematic damage at this section where the cross section against vertical demand changes, taught me thinking, what if the excessive amount of vertical tensile and compressive loading would such a thing have played a role in the damage I'm observing here? And then also we had some security camera footage from the time of the earthquake from a parking lot during that was operating during the time of the earthquake. And from the security camera footage, one can notice that the cars parked in that lot are really almost jumping in the air with this excessive level of vertical motion that's exhibited during the earthquake. And then, of course, I started checking the details of the ground motion recordings that were obtained from the region. Luckily, there is a ground motion station operated by AFA just 1.5 kilometers away from that. Station 3123 had registered the peak ground acceleration value of 0.88 G. And the horizontal components for that ground motion was on the order of 0.6 and 0.7 G around. So basically, peak acceleration demand exceeded the horizontal one. But I was more interested, not in the amplitudes only, because there is quite a significant research on the amplitudes of the vertical demands, but I was interested in the arrival time of such a large amount of vertical shaking. And I started checking the arrival times of the verticals and observed that for that specific site, the vertical peak loading tended to arrive approximately 2 seconds before the horizontal action. And then, of course, I started becoming interested, is this a common phenomenon? So do we typically have the vertical peaks arriving before the horizontal ones? And then I started looking at the arrival time differences for all the ground motion recordings that are obtained from those that earthquake sequence. And here you can see in the vertical line the arrival time difference, the data point for all the stations. So in the horizontal axis we have the station record, ground motion record index, basically. The points that are located above this zero line are the records where the vertical peak acceleration arrives before the horizontal, and the opposite one is valid for those below. But then, after such large earthquakes, sometimes the amplitudes and the ground motion characteristics itself are reported for very large clusters of ground motion recordings. But not all of those recordings are really valuable to the structural engineer. As for the structural engineers, we're typically interested in the high amplitude motions. So even when I consider the entire set of ground motion records and take a histogram of the arrival times, I noticed that the horizontal peak on the average tends to arrive earlier. I was interested, what is the case for the really intense motions? And I started looking at a threshold of 0.3 G for the vertical PGA and told that any acceleration beyond the 0.3 G vertical demand is something significant. When I checked the statistics of the arrival time differences, I started observing that for this high intensity shaking, essentially the vertical excitation, vertical peak excitation was tended to arrive on the average before the horizontal first. And this got me thinking, of course, what could be the physical reasons for that? During one of our reconnaissance visits, we were together with the Professor Kusuneki from Tokyo, University of Tokyo, and then he reminded me of the fact that as the waves are propagating from the bedrock to the surface, the P waves are the main cause of the vertical excitation exhibited at the surface, whereas the S waves are the main cause for the horizontal demand. And due to the propagation mechanics of the waves, mechanics of wave propagation, the P waves tended to always arrive earlier than the S waves. And also, for the case of saturated soil layers and so, the attenuation of the S waves were much more significant as compared to the P waves before, because of the fact that the liquids are also doing a good job in transmitting the P waves, pressure waves, but not doing a good job in transporting the shear waves, of course. So there are a number of reasons why the P waves would be expected to arrive earlier due to the mechanics of the system, and why they would be really high amplitudes in some cases. And what my take based on these observations as an earthquake engineer was the fact that as earthquake engineers, we should really pay attention to the levels of peak axial forces, both the tensile actions and the compressive ones. And probably we should really revise our estimations, revise our assumptions about the estimation of the vertical vibration modes, vertical damping ratios, and the impact of such excessive levels of tensile loading that arise before any lateral action. What will be the impact of that on the spread of plasticity, and how all this vertical motion would be sensitive to the solid foundation response of the system? As engineers, probably we should be prepared for dealing with them, because on the amplitude side, engineers, seismologists, and geotechnical engineers and so are doing a good job in characterizing the basin effects, characterizing the different rupture mechanics of the fault, for providing us the amplitudes of those vertical accelerations. And it looks like in the future codes, we're going to have better tools to estimate the vertical amplitudes of the shaking, but probably as engineers, we should also think about the arrival times and how to really account for such vertical demands properly in our analysis. Another thing that kept me thinking during those reconnaissance visits in the region was the tools we are using for dealing with such low probability and high intensity events. As an engineer, we basically take into account the presence of those events, essentially. So if we are willing to assess the performance of any structure, a facility, any critical infrastructural element, we basically open our probabilistic seismic hazard assessment results for any return period of interest. For extreme events, we go to lower probabilities of accidents, like 2% on 50 years. And we ask the engineers to simply adjust the key anchor points of the design response spectrum to get the forces, design forces that will be required for the system to achieve the target performance under such an extreme event. However, the reality of the extreme events at the site are kind of complex than that. There are several intricate connections that impact the performance of the specific facility the engineer is designing individually that are related to the boundary elements of this engineering analysis model. Unfortunately, after such extreme events, the performance of a single facility, single structure and so is determined by many other issues than just the design spectral aptitudes and design load. One of the key things that was very apparent after this Maraş earthquake to me was the surface ruptures. This earthquake had excessive amount of surface rupture that spanned over several hundreds of kilometers. So here you can see the surface displacements obtained from processing of Sentinel-1 satellite. So these are the displacements toward the satellite and away from the satellite. And you can see that there's a long range of surface rupture displacement. And on the field, it was quite observable. So I took this photo in the Chile Kahramanmaras, and you can see the surface fault rupture trace that's going on as far as the eye can see. For several hundreds of kilometers, the surface rupture could be traced. And this, for such extreme levels of events, has an impact on the behavior of the structures we have. So these kind of ruptures tend to cross many settlements, and on those settlements then such extreme levels of surface ruptures tend to deform the building. In some cases, their deformations are extreme amounts and they're directly related to surface rupture. In some other cases, these ground deformations are not directly related to the surface rupture, but instead it's related to the failure of some other connected components that are not essentially a part of the original structural system. Some cantilever wall, some retaining wall that has been designed some time ago, some neighboring building or neighboring bridge that's designed some time ago under different seismic conditions due to a past regulation and so, tends to deform the ground quite significantly. And under such extreme load levels then, when the ground support of the structure is deformed so much, that kind of a deformation exerts some change in the internal force configuration of the elements. And this changes the entire behavior of the structural system, which cannot be captured simply by adjusting the spectral accelerations. And this is some issue that we have been working for several years. And I started noticing that these extreme level of extreme shaking events were triggering such demands. And one of the severe surface deformations for this earthquake was observed at Tepehan, Altınözü. So this is the satellite photo of the region for olive tree yard before the earthquake, and this is the one after the earthquake. So basically, the entire surface deformation covered a huge area. And this is what it looks like from the drone footage. So this is an individual person. And when we chatted with the engineering geologists related to this observation, for them, it was a common feature for such extreme events, basically. From their perspective, the surface ruptures and the related surface deformation for such events, called the provincial surface deformation for the structural events, these effects were quite common to observe. What is more shocking to me was that essentially this event, this location where this extreme surface rupture had, surface deformation had occurred was called Tepehan, Altınözü. It was essentially not directly on the fault line even. So it was essentially located quite a distance from the current fault line reported by USGS. And basically, according to the geology of the slip faults at the end regions of the slip faults, it appears that for such low probability, high intensity events, such surface deformations are common to observe at the end regions. So they are really documented in geology books, but as an earthquake engineer, that was really an eye-opening for me to observe that. So another thing for the extreme level of shaking was, as very correctly addressed by the fellow presenters, was the excessive amount of non-structural damage. And once for the extreme levels of shaking, once the structure exhibits such level of shaking, we do not observe in a failure of 1 or 2 walls, infill walls or so. Basically, such levels of extreme loading triggers widespread non-structural failures. And those non-structural elements, as they're flying about from the 5th floor, from the 4th floor to the ground level, they are having a strong impact on the structural elements as well as the non-structural elements that are below. So probably in the future design codes, if we are going to guarantee the proper evacuation of the individuals after such earthquakes, so that before the aftershock sequence starts, they can easily get out, we should probably pay some extra attention to the performance of the non-structural elements located near infill, near the exit routes for our structures. And then another key thing that occurred to me at the site was that very often the seismic performance of our structures under such extreme events are controlled by the performance of the neighboring structures. So this was an old Turkish bot that was approximately 100 years old at the time of the earthquake, and this was an office building just located near to that. From the outside, actually nothing was visible. Once we got in the inside, the operator of the operator of the Turkish bot told us that the roof infill wall, roof attachment wall for this next office building had toppled down on top of this historic structure and had a significant damage to the wall, of course. And basically, these kind of observations started making me think that when we are assessing the seismic safety of the facilities under such levels of loading, we should always keep an eye on the neighboring elements. That should be always in the picture so that we can really effectively allocate our resources for risk mitigation to the correct locations. So basically, to remark that, I think reliable analysis tools for performance of structures under earthquake sequences are really needed. We should improve our understanding of the demand imposed by vertical ground motions. It looks like this is really needed, and we should enhance our capabilities of modeling the response under vertical shaking, and we should revise our strategies for mitigating the risks associated with low probability, high intensity events. I think they are a different kind of a monster that cannot be just captured by modifying the spectral design accelerations accordingly. And then I would like to thank all the institutions and individuals that helped me with that, with this research. And I will also would like to thank Dr. Hanilal for organizing this presentation, and all the SGEB members and fellow presenters for joining. Thank you. Merci.
Thank you very much, Ufuk, for this very interesting presentation. Yeah, I think we have time. So yeah, first of all, yeah, thanks to all three of you maybe beforehand for accepting to present and for the really interesting observations and your questions, outlook for future improvements and so forth. Is very interesting. And I think also for Switzerland, we can learn a lot from that. So I think we have time for some questions if anyone has. I think like either you can just write them in the chat maybe, or raise your hand. Maybe writing them in the chat is a safer option. Should we, Nikola, could you, or should we can keep recording, I guess, if it's fine with everyone. Yeah.
Hello. I can also pause if you want.
I think we can also, I mean, for those that ask questions, just in case you you switch your camera on, be aware of the fact that you're recording. Yes. I have a notification, but I don't see. I was just, thank you for the interesting evaluation.
My pleasure.
No question at all. Then maybe I start with the remark question. I liked your observations also about the non-structural elements and also the remarks that we should pay attention. What you mentioned, like getting people out safely before an eventual aftershock that will happen, and also maybe keeping in mind the different options or the different usage, maybe the escape route. Is there anything in place in Turkey with regard to non-structural elements? Like, are there typically any rules that are followed, or do you have any codes for that? Or
yes, we have a code chapter for the non-structural element design, but it's not really applied explicitly for the common residential buildings. So it's there for the ones. It's a simplified version of the ASC code in terms of classification of the non-structural elements. So we have some dynamic behavior factor. We have some factor for taking into account the expected damping level. So it guides the engineer to assess the response of the non-structural elements if it is required. For the critical facilities, for the very critical components, this is done, but not always, not for the common residential buildings. But probably in the future, we need to think about that, particularly for the non-structural elements that are enveloping the exit roads, the stairways, and the main opening of the building. So probably around those regions, we should ask the engineers to think twice while detailing the non-structural components, and also think twice while constructing them on the site, so with the proper connections, because they're quite vital.
Okay, thank you. Now the questions start popping in. So maybe we have Clotaire. You want to ask? If you're here, do you just want to ask a question, or should I read it? There.
Well, there is someone before me, I think, no?
Yeah, we do random order now, yes.
Okay. No, I was just wondering regarding these tunnel form buildings. So we expect the tunnel form buildings to fail in the direction perpendicular to the tunnel. And I just wanted to see, because I did not see the pictures you show, if you noticed failure preferentially in this direction, or if the tunnels were also damage in their main direction.
Yeah, thank you. The observations related to tunnel form buildings were very interesting for me, I should admit. I've been to several earthquake reconnaissance visits before in Turkey, but I have never observed damage in tunnel form buildings as severe as in this case. They were not very widespread, there were individual cases, but it was the first time for me to see a moderate level of damage in a tunnel form building that needs repairing. So basically that was quite surprising. The tunnel form buildings are essentially in Turkey are constructed with many structural walls in both perpendicular directions. So they're not really always in a single direction.
Okay.
But basically the formwork is producing a tunnel form at each level, but they're all the formworks attached from multiple directions of the building. So we have quite a large share of structural walls, and the damage in the tunnel form buildings are being investigated. So there are some questions about the material properties, the reinforcement detailing, and so it's being under investigation. And of course, it's a very interesting issue for us to observe and make sure that if there are any errors, so they're not repeated.
Thank you.
Thank you. Then we have two questions actually about retrofitting by Abdul Yaudi. I'm sorry if I mispronounced your name. So if any of the assessed buildings or infrastructure were retrofitted with FRP solutions and how they performed, and also following the earthquake, what can be done to the minorly damaged structures in terms of retrofitting? Or is there anything you want to add to that question, if you're still online?
Yeah, if you like. So there is a very large share of buildings that have light level of damage and moderate level of repairable damage. It's a big issue, unfortunately. It's at the moment the tendency of the governance is to replace those buildings with the newer ones with some further checks and new plans for the rebuilding of the cities. Unfortunately, for the minorly damaged buildings at a very minor level, it's difficult to make sure of their capacity even before the earthquake. So that has to be handled very carefully. But once that is properly assessed, so once it's verified that those buildings had actually quite a good resistance capacity for the earthquake before the event, then they can be strengthened, retrofitted, and their minor damage could be repaired quite well, and they could perform quite well. But then there's also the market conditions related to purchasing of the houses and the average house prices in several districts and so. Therefore, there are some issues that are beyond the capabilities of structural engineers, you know, the psychology of the residents of these buildings and so. And it's at the moment an open debate. What will be done related to the buildings with moderate levels of damage? For the minor ones, of course, they're going to be repaired, so that will go on effectively, but there's a very large portion of the moderately damaged buildings, and there are some tendencies to replace them, there are some tendencies to repair them, and it's being debated at the moment, we can say. But this is a challenging issue. It's both economically and environmentally a very challenging issue as well. So there are several aspects that should be considered.
Thank you. Then we have a question about the return period for this event. Do you know if there have been any assessments about the return period?
That's so interesting. Well, essentially, this East Anatolian fault is one of the major faults in Turkey, which is, first, it's expected to generate such a magnitude 7.8 plus event every almost 500 years. That's no surprise. So it's a very long stretch of spark slip fault and had caused devastation almost every 500 years. But the interesting thing about this event, and then of course that large fault was being monitored, its deformations were being captured, its events were being monitored and so. But the rupture did not start from this gigantic fault here. There was a minor fault that was connected to this giant, which was not being monitored. No one really cared about its response, and no one really paid attention to its slip conditions. There was no significant monitoring because it was a small fault segment. Everyone was interested in investing the resources in terms of monitoring the larger giant. But apparently in this case, this small fault segment had triggered the entire shaking. So basically all the ruptures started from this small fault located near Pazarcık and triggered the larger one. So the return period for this event becomes a little bit questionable. If everything had started on this large magnitude fault and so, everyone would say it's easily 500 years. But unfortunately, it's not. Unfortunately, it's not easy. It's showing that such large events can be triggered with relatively minor faults that are not really paid attention to. Yeah.
Okay. Thank you. Then we have a question about buildings with seismic devices, isolators or dampers, and how they performed.
Yeah, well, that's a very good question. There were several in Turkey since I think over 10 or 12 years about. There is a regulation to build the city hospitals, the largest medical facilities in cities with base isolation devices, and also some of the airports in Turkey and so are base isolated. These facilities perform quite well under these earthquakes. So for the most of the base isolated facilities, they perform quite well. I have been to only one of them in Malatya, and the users of that building told that the operations could go uninterrupted during the time of the earthquake, which is quite impressive, of course. So base isolated devices, in general, we can say that perform quite well under this earthquake.
Yes, I can also add that Safak and I were also in a couple of hospitals. I think 3, right, Safak? That were base isolated. Each one had basically no damage. They were operating after the earthquake immediately, but we were able to see the isolators only in one hospital, and they were in good shape.
In Elbistan, yeah.
In Elbistan, yeah. So quite good behavior.
Thank you. And then I see you started to answer some of the questions in the chat. So there was like getting back to the retrofitting question. So you linked a report about a building that had been retrofitted with FRP solutions that performed quite well. And also the question about the dams, you linked the presentation of one of the ERI teams that looked at
Yes.
dams. Or I don't know if you want to add something if you've seen the presentation.
Yes, I just wanted to say that so regarding the infrastructure in general, ERI had a whole team looking just at the infrastructure. So dams, power plants, roads, bridges, and so on. And I think it's quite an in-depth webinar. Regarding the dams in particular, from what I remember hearing, there was no significant damage. And they are providing power to the cities now as well. This is what I think. Some coal power plants were damaged. I mean, that's a minor damage, so they were not functional after the earthquake, but it might be repaired by now. I'm not sure what's the current state. And just one thing about the FRP or the retrofitting, from what I was also thinking about these things. From my perspective, these buildings that have non-structural damage mostly are very often RC frames, so they're very flexible. And I think the main problem is the difference in the flexibility, in the displacement capacity between the infills and the frames. So if we want to somehow improve these buildings, we would need to increase their stiffness if we want to use the same infills. Otherwise, we have to use some different kinds of infills which are going to be isolated, that have much larger displacement capacities, so we don't have this huge amount of non-structural damage in these buildings during future earthquakes. But I think FRP only increases the ductility and not the stiffness of a structure. As far as I know, I'm not an expert. So in these cases, I'm not sure if it would help a lot. If you would put FRP in an RC frame, which is already very flexible, and then everything else breaks, but the frame is okay. So then, yeah.
Thank you. I think, unless I'm missing something, we've covered all the questions that were asked in the chat, or if anyone else still has a question, last chance. If not, I'd say also we're a bit,
Hello, maybe
yeah.
Just a quick one. Just as a summary maybe of all the presentations, I was wondering, would you say that a better structural design, a better concrete, better steel requirements, and better consideration of non-structural elements will help lead to avoid so many deaths or casualties? Or would you just say that since this was a low probability event with such peak round accelerations and aftershocks, it is actually more fits the problem that this event does not occur so often?
So there was some noise in your voice. Unfortunately, I couldn't get it completely. But I think your question is about the performance of the non-structural elements under these aftershock sequences or so.
Can you hear me better now?
It's unfortunately there is some noise, so it's quite difficult to understand you.
I think.
Could you type it in the chat? Or yeah.
Yeah, I would type it.
I think I heard it okay. So Monica, please confirm if what I'm saying is not correct. But I think that your point was, is this event something that's very rare, so that it's not possible to design and build structures to withstand such earthquakes, or can we improve our codes, have better regulations for non-structural elements, then reduce the number of people dying in such events?
Yeah, thank you.
No, thank you. Thank you. Yeah, this is quite an important question, definitely. Such large extreme events are rare, but then the statistics of the past earthquakes show that essentially approximately 7% of the main shock events are followed by other main shock events in the for the onshore earthquakes, other main shock events in the neighboring faults. Apparently, such large intensity events distort the stress field around the neighboring faults. And then if those neighboring faults are already stressed approximately to their limits of being ruptured with some additional variation of the groundwaters, the pressure fields and so on, them, they tend to get ruptured. So such extreme shaking events are certainly rare, but then they're definitely followed by very devastating sequences of earthquakes, unfortunately. That's the bad news for them. So if we are responsible for designing the facility or assessing performance of facility for such an extreme event, we should apparently look at the full picture as a sequence. We cannot really say that there will be a huge level of shaking, but it won't be followed by anything. This doesn't really look realistic, apparently, from the typical behavior of nature for such events. And then both for the structural side and the non-structural side, probably if we are willing to invest our resources mitigating the risks related to such extreme events, we should handle them accordingly. Of course, we cannot focus our entire attention on mitigating them, but certainly we should do a risk prioritization and handle the issue accordingly.
Yeah, I think we can learn a lot, and I think from what the limited amount of things that we saw, I think there is a way to reduce the impact of similar events in the future, for sure. So we shouldn't just give up and say, well, this is going to happen and that's it. In earthquake engineering in general, we always have this trade-off. So we never build a structure to withstand the strongest earthquake. We don't do that for normal buildings. We do it maybe for nuclear power plants or for dams. But for residential buildings, we always allow for a certain risk. So there is a probability of something bad happening, because we assume that it's too expensive to build structures to be so strong so that nothing happens to them in any event. So there's always a trade-off. Now, where this trade-off is, I think it's also a bit of a political question, how expensive you want the new buildings to be. And but in this case, I think we can still reduce the consequences of similar events in the future, even if they're rare, because now I think we can learn a lot from this event.
Thank you very much.
Hi, may I ask if it is possible? Can you hear me?
Yes.
Yes.
Yeah, okay. My question will be, actually, it will be a bit a commentive. I'm from Antakya, an earthquake engineer. And I have some comments about the presentation from Professor Yazgan and from Nikola. That for instance, like Nikola said that pull-out thing because of the overlapping length, and the Professor Yazgan was mentioning that vertical effect on the at the bottom of the concrete. And as my knowledge, we do have capacities. We do have the capacity design and performance-based design in our codes, especially at the latest code, like the 2018 code is like a full code. It's like a good code, as we say. But what I'm seeing on the site is that, like, if you are agreeing, I would like to ask if you are agreeing with my seeing on the site. Like, we have that cold joint at the bottom of the structures, like at the bottom, that we are assuming it is fully rigid between the foundation and the column. and it is not the case on because of the cold joint. Like we are pouring the concrete after the foundation, and we are not doing it a chipping or something like that on the industry. It's not like it's not something like that. So the pulling out and the effect that you are showing, Professor Yazgan, at the normal force capacity, I guess there is a huge problem there. Like we do not care about the chipping. We do not care about like we do not give an extra attention. Do you agree with my comment on this point, or like I'm missing something else?
Yeah. Thank you, Mr. Yüksel. I agree that the connection at the cold joint that's present at the top of the foundation layer and the bottom of the concrete columns and the other walls we have, that's definitely a part of the problem, certainly. But then also the vertical and then we definitely have the principles of capacity design in our code since several years. And then also in the present version of the seismic design code in Turkey, we have the capacity design, certainly. The thing that is bothering me related to vertical excitations is actually not directly linked to the capacity design part of the issue. If during, what I have in mind, if during the earthquake excitation, at any time instant before the actual lateral demand arrives to the building, if due to a severe vertical motion is exhibited, if a severe vertical motion is exhibited, we can have excessive amount of tensile loading, and that's followed by compressive loading at those regions. If that is the case, unfortunately, we're not accounting for that explicitly in our engineering analysis. And this may or may not be an issue, I thought, but definitely this issue with the opening at the bottom has something to do with the chipping and the connection of the cold joint there as well. Probably that's a combination of several reasons. It could be in my mind, but some further research has to look into this issue. I definitely agree. So the point you mentioned, it cannot be ruled out. It's definitely a part of the reasons.
Okay,
Yes,
thank you very much. I think it made me like enlightened now, but I understand why you were like mentioning the vertical motions, because like, yeah, thank you very much.
Thank you.
Okay. Yeah, I think maybe also for time reasons, we already went over a bit to not stress too much of your time. I think, yeah, at least there were no more questions in the chat. So thank you very much again to all three of you for this these really interesting presentations and the discussions, everyone. And yeah, sorry for the technical issues at the beginning. So this was our first trial. So you were kind of the how do you call them, the trial animals? But in the end, all went well. So thanks a lot for the presentations, and hope to see some of you or all of you for the next seminar that we plan with the SGEB, which is now, I forgot the date, but it's after the summer break, so to say, in mid-September. So hope to see some of you there, and have a nice afternoon, everyone. Thanks.
Thank you.
Thank you very much.
Thank you.
For the
It was a
questions.
great pleasure. Thanks a lot. Thank you.
Pleasure. Thank you.